Welcome to the fourth lecture of the course Mathematics and Statistics for Infectious Disease Outbreaks. So let me start by putting up the slides. Let's see now, view. Oops, sorry, I forgot an important thing. I should have put share slides first of all. Now I think you can see my screen, and then here is my slide. And here are the slides. So today I will talk a little bit about estimation of R0, both when you observe the whole epidemic outbreak and when you observe only the beginning of it. And then I will connect back to my earlier lecture. I think it was lecture number 3, when I talked about problems of estimating the generation time distribution and how that can affect the estimation of R0. And then at the end, I will talk about effective reproduction numbers. And I will have a break sometime in the middle. We will see when that happens. Okay. So much of today's talk is about doing inference or estimating things. So a few general words. I mean, this course assumes that does not assume that you have taken any course in statistical inference, except the little that is taught in high schools. So this is at a very low level, but still important to have in mind. So when we do stochastic modeling, or for that matter, deterministic models, so more or less any mathematical model, then the situation is as follows. So suppose we have a model, and suppose we are given some parameter values, then if we do our analysis correctly, we can say what are the likely outcomes. For example, if you remember my first lecture, I said that if we know what R0 is, there was an equation saying how many that will get infected. Now, if we're statisticians, things are in the opposite direction. So instead of knowing the model and knowing what the parameter values are and saying what the outcome will be, instead we observe the outcome, and from that we want to find out what model, but in particular what parameter values agrees with our observed outcome, or what parameter values fits with our observed outcome. And that is called estimation. So how do we estimate the parameters given some observation? For instance, connecting back to the final size equation, I can write what the final size equation was, by the way. So in case you don't remember it, I have to share, stop sharing slides, and then I share slides again, but now with my whiteboard. So here we see, if you remember correctly, the final size equation was 1 minus this thing called tau should equal e to the minus r naught tau. Sorry for my handwriting, but it's hard to do it on this writing pad. So in the first lecture I said, if we know what R0 is, this equation here determines how many that will get infected. So I think I had an example where R0 was 1.5. Then the conclusion was that tau should equal approximately 58%. However, when we are statisticians, we don't know what R0 is, but we observe an outbreak. So then the question is, okay, so suppose, for instance, that we observe that 20% got infected, that is tau is equal to 0.2. What should R0 be then? Well, actually, we can use the same equation to derive an estimator for R0, and that is part of today's contents. Now I go back to my lecture notes. They are here. Yes. So for instance, suppose that 20% got infected during the outbreak. So we observe a full outbreak. Then the question is, what is R0? I will come back to that later. So now we are talking about estimation of, so this is more or less in general. Stochastic modeling tells us how likely outcomes are and which outcomes are likely. But if we're a statistician, we observe the world, the reality and outcome. And then from that, we want to infer what are some parameter values that fits to our observation. They would be our estimates. So suppose that we observe some epidemic outbreak and we want to estimate some parameters. It could be the transmission probability to a particular individual, it could be R0, or it could be something else. How do we do that? Well, of course, this depends on what type of data we have. So first today, I will consider final size data, meaning that what we observe is how many that got infected and how many that were not infected during the outbreak. So at the end of the outbreak, how many were infected and how many did not get infected. Beside knowing this, it's important to know if there was prior immunity or not. That is not not part of the random outcome, but it's an input to the start of the outbreak. So that we also need to know. That could perhaps be obtained from some additional data, but I will not talk about that as much. Okay, later I will talk about one big outbreak, but let's first do a simpler case. Suppose that data comes from many small controlled experiments. How do we do then? Well, in fact, then inference is a little bit easier. This is a situation that, for instance, happens in several, let's say, vaccination studies or also controlled experiments among animals to see how transmittable the disease is and so on. So of course, it's an idealized situation, but anyway, suppose this is the way it goes. Suppose we have quite a lot of units, each unit consisting of 2 individuals. And suppose we start the experiment by having one of them initially infected. So the situation looks as follows if I write it on a pad. Let's erase this. Oops, clear. Okay. So suppose we hence have several Oh, sorry about that. Let's clear that. That was too ugly. So here is one unit where we have two individuals. Then we have another unit where we also have two individuals, and a third one where we also have two units. And it goes on like that. And suppose further that there is no infection in between them. And suppose we start with one individually infected in each of these units, randomly chosen who was infected. So suppose we start our epidemic like this, and then we run it, we let things have happened. So suppose that the result is that of our n units, for some reason I here call them households, it could be households, but anyway, they're of size 2. And suppose that out of the n households, m get infected. So maybe we have 100 households, or let's say we have 50 households and 32 got infected. So m is 32, that is the random outcome. N is 50, that's the number of pairs or units or households. That's non-random, we chose that. And suppose that 32 of them, the second individual was also infected, and in the rest, which hence should be 18, the other individual was not infected. How do we estimate the transmission probability within such a unit? Well, that is very easy. If 32 out of 50 resulted in infection, we estimate the transmission probability by 32 divided by 50. And I put a hat here because I don't know what the true value is, but I estimate it by 32 divided by 50. If someone else did a similar experiment, maybe also having 50 units, probably they would not have exactly 32 where an infection took place, perhaps 29 or 36. But anyway, so this is an estimate which will be different if you repeat your experiment. So anyway, the estimate is 32 divided by 50. What is nice is that if these units were isolated as we assumed, then their outcome is independent of each other. So we have 50 experiments, independent experiments that could result in each of them results in transmission with probability p, and no transmission with probability 1 minus p. So in total, the number of units where an infection took place is a binomially distributed random variable. And it is well known how to produce a confidence bound for such an estimate. It is outside the scope of this course, but anyway, it is the point estimate that we had before, and then we add some uncertainty. And this thing here comes from the normal distribution, because when n is large, the binomial distribution looks like the normal distribution, and inside here is the standard deviation of the estimate. If you have taken a course in probability, you know that the variance of a binomial random variable is n times p times 1 minus p. But now here we have divided by, this is not a binomial random variable, it's a binomial random variable divided by n. So for that reason, the variance is p times 1 minus p divided by n. And then we take square root because I have the standard deviation. So this will give a 95% confidence interval if we choose alpha equal to 0.05. And then we have the well-known normal quantile for 95% confidence intervals is 1.96. So an exercise for you is to compute this confidence interval if we assume that we have 100 units and 27 of them got infected. How would you estimate P, transmission probability, and what would be your confidence bound? Okay, that was if we had several small outbreaks, but for most human diseases, or for human diseases, when it's not a control experiment, we typically just have one large outbreak. Or we could have a couple, but most of the time we just have one. So here I now explain how to do it then. So assume that we have a homogeneously mixing community and that we have no preventive measures. So this is not the COVID-19 situation. Perhaps it could be influenza or some other disease. However, as for now, I also assume that we have no immunity. Okay, from before we had this equation for the final size, assuming that everyone was initially susceptible. This was the equation for the final size. So then the inference is the other way around. So we observe tau, or tau tilde is our observation. That is how many got infected or what fraction got infected. Then the question is, what is R0? So what we do is we rewrite this equation to put R0 on one side. It was not possible to rewrite it to have tau separately, but it is possible to rewrite this equation to have R0 separately. And it's simply minus the natural logarithm of 1 minus tau divided by tau. So this is, here tau is the limiting final size probability. But now we have an observation of tau, which we call tau tilde. So then our estimate of the basic reproduction number is simply this expression where we insert our observed value of tau. So here's another exercise for you. Do this, assuming that 20% got infected. How do you estimate R0? As for now, we will skip standard deviation, but it is possible to obtain standard deviation using some fairly complicated probability theory, which I will not explain the underlying theory, but maybe I will give the standard deviation later. This estimate assumed that everyone was initially susceptible. Suppose that's not the case. How do we do then? So suppose instead that the fraction R was initially immune. So this is more likely a situation with seasonal influenza, for instance. I don't know exactly, but maybe it is known that before the influenza season, maybe 50% of the community are immune. That I don't know, but that is something that one can try to find out by taking testing for antibodies against the influenza, for instance. So suppose that a fraction R is... Suppose that the fraction R was initially immune, and that we know what R is from before, and that fraction of... and then suppose that... then we knew earlier when I talked about modeling that if a fraction R are initially immune, then the fraction that gets infected among those who are initially susceptible satisfy the following equation. So if we have some immune people, we instead go to this equation and we solve this equation for R0, and it looks like this. And then, as before, we replace the limiting theoretical value for tau by the observed fraction infected among the initially susceptible, and that will be our estimate of R0. Note, however, that here tau should be the fraction infected among those that were initially susceptible. So that's not the population fraction that got infected. The population fraction that got infected is this quantity. So another exercise is to do the same thing as the previous exercise, but now to do it assuming that 50% were immune. So assume 50% were immune, then an outbreak takes place, resulting in 20% getting infected. And from that, you should first compute what is cont'd and then estimate R0. Okay. I think I will end the first part of the lecture here, and I will soon start the second part.